So when we disconnect this branch, RL branch, from the source, current in steady state regime when t tends to infinity, and voltage drop will be equal to 0 because it is disconnected from the source. But this current and this voltage drop will exist during the so-called transient processes. Why? Because due to current flowing through this inductance, nevertheless voltage drop across this inductance was equal to 0. Nevertheless, current which flows through this inductance creates magnetic field energy, and this stored magnetic field energy was the source of natural component of current after commutation. But this voltage drop will be dissipated in this resistance, and after all this current will be equal to 0 as well as voltage drop across this inductance. So let's draw graphs of these values of current and of voltage drop. You see, as for current, we do know that before commutation it was equal to E over R. It is here, yes? And when t will tend to infinity, this current will be equal to 0. Okay. But between these two values, it will be transient processes, smooth transient processes. You see, at the moment t equal to 0, at the moment of switching, we have smooth transaction from value E over R. It is the same at t less than 0, this moment, and the same at the first moment t equal, first moment t equal to plus 0. Sorry, the same value, okay? And then this current will change in accordance with exponential law and it will be almost equal to 0, 1% of initial value at the time moment 4.6 tau L, okay? Something like this graph, this exponential function. You see, it changes smoothly from level 1 to level 0.37 when t equal to tau L, to level 0.13 at t equal to 2 tau L, and so on. So we have such a graph for current in this considered case. And let's depict also changing in time of this value of voltage drop across inductance. We have such a function, and we can see that at the first, you see, before commutation, as I have told you, voltage drop across inductance was equal to 0 because it was steady state DC processes, and at such processes inductance behaves like a short-circuited part of schematic. So it was equal to 0, and it will be equal, this voltage drop will be equal to 0 when t will tend to infinity, because this branch will be disconnected from the source. So it was 0 and it will be 0. But between these two states we have these transient processes, and as voltage drop across inductance is not dependent parameter, is not independent parameter, it is dependent parameter, it may change abruptly, you see, and it really changed abruptly. It changed from 0 value at t less than 0 to volume minus E at t equal to plus 0, and then it change in accordance with exponential law. It diminish up to 0 level. And why physically, why it is changed so steeply? Why it is changed so steeply? Because it was necessary to retain the same volume of current when source was abruptly disconnected from this branch. Source was disconnected. So when source was connected, it was some current here. Then source was disconnected, and we have forced component equal to 0, but natural component should have such a volume to retain the same current here. And for this to retain this volume, voltage drop across this inductance was equal to minus E. Voltage drop, you see, when EMF, when we replace this EMF by voltage drop, it was taught in previous semester, its sign should be changed by the opposite. So here voltage drop across inductance was equal to minus E to provide retaining the same level of current as before commutation and after commutation. Then at last, let's consider physical meaning of transient processes. Physical meaning it's during period of transient processes, energy that has been accumulated in the magnetic field of inductance before the moment of switching is released as heat in a resistor. You see? So this energy is spent irreversibly, and it is transformed to heat in a resistor. And let's prove it. Let's calculate energy that is released at heating during these transient processes. Let's designate WT, its energy which is spent for heating. Yes, and it's an integral from 0 to infinity of energy. It was in previous semester. Volume of energy, it's R multiplied by IL power 2 by dt. Okay, this is energy. Yes, sorry. This is power, and power multiplied by time and integrated over this all time period, it will be energy which is released in this resistor. Let's substitute here values of IL power 2 of this which we got a solution of differential equation which depict electrical processes in this contour after commutation. You see, this value should be substituted as current power 2. It will be E power 2 over R power 2. It may be put before integral because it's constant, does not depend on time. These are also before because we consider linear processes with constant resistances, capacitances, inductances. Then you see this R, it is here, this IL power 2 coefficient in the second degree also before integral, and integral under the integral it will be this exponential function in the second degree. You see, second degree it is this 2 appears in this power, so it will be easily minus 2r over L multiplied by t. Okay, how can we calculate such an integral? It will be, you see, it will be r, and r power 2 can be cancelled. Here r will disappear, and in denominator will be r in first degree. Yes, and this integral from exponential function equal to exponential function, but as here was integral by dt, we should multiply and divide this dt by coefficient to power of this exponential function. So it will be minus L over 2r, and it is dividing of this expression by this coefficient, and when we multiply by this coefficient we have exponential function d from this argument. So it will be just this integral from such a function is just this exponential function. Here we have this minus L multiplied by e power 2 over 2r power 2, okay? Then this refers to this coefficient, then this exponential function, we should substitute here limits 0 and infinity. When we substitute limits infinity, this exponential function will be equal to 0, because e in minus infinity degree equal to 0. Yes? Then minus and substitute this lower limit. It will be exponential function in 0 degree. It will be 1, a unit here, minus 1. Okay? So this minus and this minus will give plus, and we will have here just L I e power 2 over 2 r power 2. Okay? And if we can rewrite this expression as L over 2 and this e over r equal to IL before commutation, e over r, okay? It was current before commutation. So it will be L over 2 multiplied by IL power 2 from minus 0. So what we will have here, it's LIL power 2 over 2, it's energy of magnetic field, and as current here is before commutation, so it will be energy of the magnetic field before commutation. So what we've got here, it is proved here that energy which is released in resistance in this schematic equal to magnetic field which was stored in this inductance before commutation. You see, we have here magnetic field, we prove it before commutation. So it is proven that in the transient processes of current flowing through this branch, this energy that was stored in this inductance before commutation has been released as heat in resistance, which is connected in series with this inductance. Okay, so physical meaning of transient processes is spending of magnetic field energy stored in inductance in resistance as a heat. So it is over, but I would like